Is it actually recording? I guess it is. Okay. All right. So we're doing a new, whoops, I forgot to plug in. We're starting a new module today, which is some circuit analysis. And we've done a bunch of it already, but we're going to go ahead and sort of formalize it a little more or do a little bit, a slightly different approach maybe than what you may have seen in the past once the screen comes on. There we go. So nodal analysis is just KCL, which is the sum of the currents into the node equals the sum of the currents out of the node. We've already started that a little bit, but just to recall or refresh, we know that a node is a location, if you will, where two or more devices or elements or components, whatever you want to say, come into contact. So in this circuit on the left, it's maybe not as obvious to see the nodes. So on the right one, it's a lot more obvious, but this is just a recommendation in terms of making it easier to spot nodes. What I try to do is I just do like a bubble cloud and I kind of just shade in until I get to a device, right? So when I hit a device, I have to stop my bubble cloud and continue on. So I know that's one common node. I do the same thing over here. Two. And then I always want to make sure that all my common connection points are sort of bubble clouded. And I see that I have three separate and distinct sections where I have devices I connect to. So that's three nodes. If you prefer, you can do the other approach, which is to really kind of make it scream at you and then kind of draw things without as much sort of open wire, if you will. But I don't suggest that because I find it easier just to take a bubble cloud, or you can take a highlighter if you want, and you can just highlight the spots for the common node, and then you can go ahead and do that. I like bubble cloud because if you screw up when you're highlighting, you're kind of one and done, right? But if you use a pencil and you bubble cloud it, then you can just go ahead and you can erase that fact that you may have made a mistake. All right. Probably won't make too many mistakes when you do it, but you get the idea. So whatever you want to do is worthwhile. But the reason why you need to know the nodes is you need to know how many KCL equations you're going to write. So in this example, we have three nodes. How many KCL equations do we need to write? Two or three? That's right, but what's the reason why? I read it in the book. You read it in a book a long time ago? It's zero on the clock. It might be zero. A better way to describe it, this is our reference node. So everything is in with respect to a reference node. So it could be zero, but there's nothing saying that that can't be, 100 volts. So the actual voltage, if you were to go to measure it with respect to ground or reference, could in fact be, a much higher potential. But oftentimes in this class, we'll assume it's zero just to make the math a little bit easier. Okay. But it doesn't necessarily have to be. So when we do our nodes, we specify the node numbers, 1, 2, 3, 4, whatever, how many you have. The reference node, you call it out as the reference node, just because, again, you don't want to write a nodal equation for the reference node because you can't really. You don't really have the ability to do that. And you don't want to because it's just going to add some confusion and complexity. And then it's up to you. You can specify assumed voltage drops in that direction, the plus minus. I prefer to show currents going from what I hope is the correct direction for current. Because I'm not really doing voltage addition and subtraction for nodal analysis. I'm doing current, right? So knowing that that's V1 and V2 isn't as useful to me to know the current that causes V1 is in the top to bottom direction. Similarly, the current that causes voltage drop V2 is in the top to bottom direction. And why do I want to know directionality? Because KCL is the conservation of matter. It's the sum of the current into the node equals the sum of the current out of the node. So once I know the current directions, I have to now just figure out what the currents going in and out of the nodes are, and then I can go ahead and do it that way. Okay? The V1 and the V2 literally are just whatever voltage you want to call it. It can be V1 because this is a 1, and V2 it's because that's a V2. You could call it VA, VB. You can call it whatever you want. It's just helpful to make sure that you use some sort of a approach that it always sort of shakes out what the results are going to be. Meaning it's easy to find, hey, this is node 1, this is node 2. All right, so we'll continue with this problem. And we know that we have to write 2 nodal equations, right? Because we have 3 nodes and one's our reference, so we write 2 nodal equations. So the first thing we do is we're going to assume a current direction. And this is just assumed. We have no idea of knowing if this is right or wrong. We have zero ability to do that. But it doesn't matter. As long as we account for them and we make sure our sign conventions are correct, then we're in pretty good shape to do this problem. All right. So now I'm going to go ahead and I'll write this here, but we'll actually just do it this one time. And after that, we'll actually make it a lot easier where we'll do it from the perspective of just writing it in an equation. This current over here is V1 minus the reference voltage. So for now, we'll call it 0. And we're going to divide that by 2. That's that current. This current over here is V2 minus 0 divided by 1. And to solve for the current through the 5 ohm resistor, all I'm doing is Ohm's law. I'm looking at the difference in voltage across the element and then dividing by the resistance. The difference in voltage is V1 minus V2, and then I divide by the element, which is 5. And that's that current here. So now for V1, we're going to use the sum of the current into the node equals the sum of the current out of the node. But again, we can do this 100 different ways. The current into the node is 3.1 amps. No units there, or it does technically have amps, but I don't have to multiply it or divide it by anything. It's just 3.1 amps. Now the sum of current out of the node is on the other side of the equality. So I'll just take this first current over here. This is current out of the node. So that's that V1 over 2. And I drop the 0 because V1 minus 0 is still V1, right? So it just becomes V1 over 2. And then the other current that's exiting that node is the current through the 5 ohm resistor. So I'm going to add plus V1 minus V2 over 5. Okay? Everybody follow that so far? Hopefully review. Let's do this one now. So we have this current, this current, this current. So this one was V1 minus V2 all over 5. This one is V1 over 2. And this one is V2 over 1. Now, the current into the node is what? There's no current into the node. So technically, if I wanted to be 100% right, we would call that 1.4 plus all the other currents out of the node, right? Because 1.4, well, actually, let me back up. This says minus 1.4. So this would be current out of the node is minus 1.4. Right, that's showing us current out of the node. So let me cancel that out just to make it easier. So 1.4, just using the arrow, it's a negative number, no problem. Then I've got the current going through the 1 ohm resistor. So that should be, this is a typo, sorry about that. That should be V2 divided by 1. Here, let me fix it this way. I can just fix it just as quick this way instead of trying to. Stop moving. All right. So this is, I got to delete that because I can't see it. So this is V2, right? Divided by 1. And this is going to be, we'll move this to the other side. So that's 0. And we have negative 1.4 plus, there we can fix that. Easier to fix it that way. All right. Wait for it to finish saving. And then duplicate. Turn this off. Okay. So my current out of my node, I'll just show those. Negative 1.5, 1.4 plus V2 over 1 plus, now I should have, yeah, so this current right here, this is plus V1 minus V2 over 5, correct? Now, anybody have any heartburn with how I set that up? Because this current here is V1 minus V2 over 5. That's for current going from left to right. And the reason why we do that is because we assume from a higher potential to a lower potential is in the positive direction. So it's V1 minus V2 divided by 5 is the current from left to right. Let me make sure everybody understands that. The current be going in the direction from left to right has to go from a higher potential to a lower potential. So I have to take V1 minus V2, and then I divide that by 5. If I did V2 minus V1, then I'm assuming current flow in the opposite direction because I'm assuming that V2 is at a higher potential. So pretty important that I go ahead and set it up this way, at least initially. We'll show you another way that makes it hopefully a little bit easier. And then we have these answers. All right, so here is how I suggest you do these problems. So we have two equations. Let me launch whiteboard real quick. All right, so my first equation is here. So I can do a screenshot. And I'll put that over in whiteboard and I'll paste it in here. That's my first equation. And then my second equation, I'll do another screenshot. Okay. These are my two equations. Now, probably most of you, what you would do now is you'd solve for either V1 or V2 and substitute into the other equation, correct? All right. I'll show you another way with matrices that makes it a little more, I think it takes a little bit of time to set up, but it's more efficient and it kind of gives you everything in one fell swoop. So let's take a look at our first equation over here. And we see it's got a bunch of V1s and V2s in it. I don't know what V1 and V2 are, so I'm going to write those as variables, multiplying a number, and then I'm going to set that equal to what I know. And then I'm going to do that for the same thing for the second equation. So let's go ahead and expand this. This is V1 over 2 plus V1 over 5 minus V2 over 5. That's going to equal 3.1. All I did was just get rid of the V1 minus V2, right? So I just took the numerator and I broke it up into individual terms. At this point, I'm going to collect all the V1s together. So moving along, I have V1 over 2 plus V1 over 5 minus V2 over 5, collecting all the V2s, equals 3.1. At this point, I'm going to factor out my V1. and I'm left with 1/2 plus 1/5. And over here, it's pretty easy, right? I don't have to really factor anything out because there's only one V2 term. And that's going to equal 3.1. Now, the last thing that I'm going to do is I'm going to put the 1/2 and the 1/5 onto a common fraction just because it makes it a little easier to enter into the matrix. You don't have to enter it in, you don't have to do this extra step, but I'm lazy, like I said, so it makes my life a little bit easier. So this is V1 times, we know a common denominator is 10, and then this is going to be 7/10 minus V2 over 5 is going to be equal to 3.1. Any questions on how I got that equation? It may have been a minute since you did common denominators and stuff like that and put them under, but it's a pretty important thing that we need to do here just because it makes entering our matrices much, much easier. So far, so good? All right, let's do the second one. So I'm going to move the negative 1.4 to the other side. So I've got equals 1.4. And then I'm going to take the V1s and move them out front. And then I'm going to take the V2s and sort of lump them together. Plus V2 over 1. And then minus V2 over 5 is going to equal 1.4. Now I can see that I can skip this step, and I'm just going to go ahead and set them up in factored form. So I have V1 over 5 plus V2 times 1 over 1 minus 1 over 5 is equal to 1.4. Okay? We good with that? All right. So now we can set it up in our form where we're going to combine the V2. So that's going to be plus V2. Now common denominator is 5. So we have 5 over 5 minus 1 over 5, which is 4/5. And that equals 1.4. Okay, that's my second equation. I'm now going to go ahead and put these in matrices to make it easy to do calculation. And how you do a matrix is you start by sort of giving yourself a little bit of space to work with, but most importantly, your unknown variables are going to be in what's called a column matrix. You just have one column. You can have multiple rows, but I only have one column. And then I also include what it ends up equaling, 3.1, 1.4. Now I just look in here and I see the numbers. Well, what multiplies V2? 0.7. What multiplies V1 in this first equation? Minus 1/5. What about over here? 1/5. And what about over here? 4/5. Okay. Everybody see that? Sure. Say that again. Yeah, sure. So when you're doing matrices, all I'm trying to do is I'm trying to take the row, so this is the first row in that matrix, and I'm going to multiply it by the first column, and then I just add the terms. So what I see, what multiplies V1 in this first equation is 0.7. What I see, what multiplies V2 is minus 1/5. That gives me my first row, and then I can set it equal to whatever it's equal to, which is 3.1. I do the same thing for the next one. V1 is multiplying 1/5. So now I've moved to the second row. And 4/5 is multiplying V2. And then that equals the 1.4. Okay. Now, one thing I'm worried about, normally these are the same polarities. So let me just go back and make sure that I did these correct. So we have V2 minus, yeah, and then V1 minus V2 over 5. Ah, I didn't do it right. What did I do wrong here? What did I do incorrect? I see I made a mistake. Well, I added 1.4 to both sides, so that's how I did it. Well, in this equation right here, I made a mistake. What's the mistake? Anybody see it? That's current in, right? These two are current out. So this right over here, whoops, that V1 minus V2 over 5 should be on the other side of the equation, shouldn't it? So let's go back here and get this out of the way. So this is not plus, but it equals that value here. Okay, does that make sense? So it's checking it again. Let's see the sum of a current out of the node. In this case, we have 1.4, negative 1.4. Oh, it just died. Why did it just die? Really?
Yeah, you have to be in good state for that.
I don't know. Should be. Hmm. I don't know. I mean, maybe that's the fancy technology. It'd just be easier if I could mirror cast, but I don't know if this one is set up that way. All right, so let's go back to that. Minus 1.4 plus V2 over 1 are the currents out, and the current in is V1 minus V2 over 4. So let's go back to whiteboard here. And should we start over because of the mistake on the second one? We know this first one is correct, right? We're pretty comfortable with this one. So let's erase this stuff right here because we have that one sign change. And then we'll fix it because it does give us a little bit of, it would have given us a goofy number. All right, so let me go back here and copy that. Or screenshot it. Paste it into here. All right, so now I'm going to go ahead and move the 1.4 to the other side. And I'm also going to move the V1 minus V2 to the other side. So what happens when I move the V1 minus V2 over 5 to the other side? It becomes a negative. So all I have to do is do that, right? I just put a negative out front, which means the V2 and the V1, they swap polarities, correct? So instead of V1 minus V2, it's V2 minus V1. So then that becomes V2 over 1, and that equals 1.4. Now I'm going to go ahead and collect my terms. V1 over 5 plus V2 and factor 1 over 1 plus 1 over 5. And I continue. Oh, that equals 1.4. I've got to keep my 1.4 in here. And then what we end up with is negative V1 over 5 plus V2, and that becomes 6/5 equals 1.4. Now I could do my matrix again. So I set up wide matrix with V1 and V2. This is 0.7. This is negative 1/5. This is negative 1/5. This is 6/5. And that's equal to 3.1 and 1.4, getting us back to our matrix. Okay. So do you remember when I said I knew that there was something wrong because of the fact that those two signs weren't the same polarity? And so when you're doing these somewhat straightforward circuit analysis. The thing you can do to check their work is what's called the off diagonals. If the off diagonals have the same sign, and the same number actually, so if it's the exact same number, you're probably in pretty good shape. Because it didn't have the same sign, I realized that, okay, there must be a mistake there. All right, so now all I need to do to solve for V1 and V2 is I've got to get rid of this term over here. We'll call that our R matrix, our V matrix, and our I matrix. So how do you get rid of R when you're just doing standard Ohm's law? That's actually R inverse, right? It's 1 over R. How do I get rid of R inverse? Ohm's law, right? V over R equals I. How do you bring the R to the other side? You multiply R by both sides by R, correct? You got to do the same thing in matrices, but matrices don't allow you to multiply, or I'm sorry, they don't allow you to divide, right? Because we'd have to divide by the inverse of we have to divide by that R term. So technically what we'd have to do if we were doing, if we were dividing by, right? This is our I matrix. We would have to divide both sides by R minus 1. You can't divide matrices, but you can multiply by the inverse, can't you? So what I'm going to do is rewrite R1 raised to minus 1. And I want to get rid of my R inverse by multiplying by the inverse of R inverse, right? And here's the thing. In matrices, I have to be very careful about dimensions. R is a 2 by 2 matrix. It's 2 rows and 2 columns. V has 2 rows and 1 column. And I has 2 rows and 1 column. Those are the dimensions of the matrix. If you can't remember, it's rows by columns is how you define the matrices. Okay? Now, for matrices to be able to be multiplied, the inner dimensions must be the same. Those have to be exactly the same. And in this case, it's good that they are, right? It's 2 by 2. And the resulting multiplication is the outer matrices, which is a good thing because we said a 2 by 1 is on the right-hand side. We should have a 2 by 1 when we multiply it out. When I take the inverse of R1, it has to be a square matrix, and the result is going to be R, which is going to be a 2 by 2 matrix. So if I want to make sure my dimensions check out, meaning I can multiply correctly, hopefully what you see is I darn well better multiply to the left or all the way in front of my my approach here, because this here, those two dimensions have to work. It has to be a 2 by 2. And my resulting matrix is going to be a 2 by 1. Let's go back and check and see if I did it the other way. So this is my R inverse matrix. This is my voltage matrix. What happens if I multiplied by my R matrix over here? Any problem with that? What's the problem? Yeah, these two are not the same, are they? So if you tried to multiply those two in your calculator, you'd get a dimension there. It would actually burp at you and say, we can't multiply, so you can't do it that way. So you can't multiply and not have the dimensions work out for you, okay? Very, very important that that works out. So you have to do it over here. And because, and I don't know if this is the right term, I'm pre-multiplying on the left-hand side, right? I'm multiplying everything to the left. I darn well better multiply to the left side of my I matrix. So let's check that again. So my R matrix is a 2 by 2. My I matrix is a 2 by 1. Does that check out dimensionally? Sure does, right? And then my result is here. So that's the kind of the most confusing thing about matrices is why isn't this working? I've got it set up right. Why am I not getting good results? The reason why you might not be getting good results is because you don't have your dimensions or you're not multiplying in the correct order. So if I look over here, I've got this equation over here. So I'm going to rewrite it just to make it a little bit neater. So that's minus 1/5, that's 0.7, minus 1/5 and 6/5. Multiply that by V1 and V2, and that's going to equal 3.1 and 1.4, right? Just rewriting it over again. Now I'm going to pre-multiply both sides by the inverse. And do you know what you end up with when you multiply a matrix by the inverse of a matrix? You end up with the identity matrix, right? So if I multiply R inverse by R, I'm going to get the identity matrix. And the identity matrix is just the same thing as multiplying by 1. So when I do that, I'm going to multiply both sides, pre-multiply both sides by R. I'm going to have V1, V2, which is my identity matrix. And then this is R times 3.1 and 1.4, where R is equal to the inverse of R to the minus 1. Okay. So the best way to show that being done is to actually do it. So remember we talked at one point about MATLAB, right? Using MATLAB. So we're going to use MATLAB. So we'll call this matrix R inverse. And that's going to be equal. And the way you enter matrices, I use a bracket to indicate it's opening a matrix. This is 0.7. This is minus 1.5. That's my first row. To move to my second row, I use a semicolon. So in between elements in the same row, so if you're moving from one column, you can either use a comma or a space. Up to you. I like to use commas because it kind of screams at me saying, okay, I've moved to the next one. Sometimes when you're looking through things quickly, sometimes you don't notice the space all that well. Like sometimes it just kind of gets blurred with it. But I see the comma, it looks more obvious to me. So that's my first row in my matrix. My second row is going to be equal to minus 1/5 and 6/5. Now I'm going to close the matrix and I'm going to hit enter. Does that look like my original matrix? It does not because I put point here. I meant divide by. So does that look like my original matrix? 0.7, minus 1/5, minus 1/5, and 6/5. Looks pretty close, right? Okay, so now my current matrix, I'm going to enter an I, and that's going to be equal to open bracket 3.1, and then I'm going to use a semicolon because I'm moving to the next row. 1.4, close the bracket. Now I'm going to move this up. Does that look like my second 3.1 minus 1.4? Now to solve for my voltage matrix, I'm going to take the R inverse and invert it. So R underscore inverse. And I'm going to raise that to the minus 1. And then I'm going to multiply that by my I matrix. And those are my two voltages. 5 for V1 and 2 for V2.
So I have to say the question.
Sure.
So what if I was being lazy and I put in again is the first part and then for that first term the 0.7 like I didn't wanna, yeah, I wanted to do just like a 1 - 0.3 instead of put that in. Would it just read that as the equivalent of 0.7, or would I have to exactly put in 0.7?
Let's try it. 1 minus 0.3, right? Is that what you're asking?
Yep.
Still works.
Alright.
It can do inline calculations. You can also do, instead of entering, 0.7, I could have did 7/10, because you can see over here, I did -1/5, right? So it can do pretty much any reasonable calculation inside the matrix.
I was just wondering if there was like identical to calculator that I do. Like in the sense that like if I didn't wanna do, if I wanna do like 3 sine 30 instead of just like putting the first 5 significant digits of whatever that is.
You can do it exactly the way you said, but I will just challenge one thing you say. You want to see if it's identical to the calculator. No, the calculator copied MATLAB. MATLAB was around first. So a lot of the calculator stuff, the way you enter stuff in, and using brackets and semicolons and commas is how, if you have like a TI-89, unless you use the matrix editor, that's how you enter in. I don't know if that's an 83 or an 89, but you can enter matrices in using brackets, commas, and semicolons. Anybody ever done that in a TI-89? Yeah, it's the more efficient way to do it, but this is how MATLAB's been doing it for 50 years. So I think TI just said, let's just go ahead and copy what they did because people are somewhat familiar with it. All right, I'm going to pause because this was a lot, maybe. This may be a lot depending upon what you were taught in terms of linear algebra. It might have been this much, or it might have been this much. So I need feedback. I need to know how much people have seen, how comfortable are they with it, et cetera, because depending on, well, no matter what, you're going to be using matrices a lot more as you progress in your college career, but it just depends on the pace of how we go through material, and setting up matrices will be a big, that will give me a lot of information. So what do you say? You experts at linear algebra? You had a thimble of them out? Been 20 years? Yeah, as I say, most of the time, if you had linear algebra, probably in high school, right? If you covered it, I don't know if they do anything in MAT 122, which is our pre-calc class here. That's right before we take 126. Sometimes they cover it, sometimes they don't. Did anybody take 122 here, MAT 122? Did they cover any linear algebra at
A
all?
little bit, but it was at the beginning.
Yeah,
We covered a tiny bit of matrices at the end of our pre-calculus class that we see.
okay.
But it wasn't really a crazy amount.
Okay. But really, the nice thing is, if you had a little bit, this is pretty much what we need, right? We just need a little bit, but you might not have remembered, the multiplication has to match the rows and the columns. And then the result is because you haven't done it in however many years, right? But we will do that a lot in this class, unless, and this one's not a big deal, you're more than welcome to solve simultaneous equations and substitute in. You're welcome to do that, but we'll at least be able to do a 3x3 matrix in this class, which now you have to solve 2 equations and just keep back calculating and all that stuff. It gets to be a lot of work. And if you take and it depends on what your concentration is. If you take a class from me in power systems analysis, we have no choice but to do matrices. Anybody want to guess why? Remember how we just did a 2-node problem? What if I did a problem that had 2 million nodes? You're going to solve 2 million simultaneous equations by substituting back in? Probably not, right? So at some point, you're just going to take advantage of the math and you can populate things in the matrix because it just is going to be so much more efficient to do it. So doing 2, maybe 3, you can solve simultaneous equations. But once you start getting 4, 5, 6, you're just way better off to do a matrices. And depending upon, how far you want to get into your analysis, using linear algebra, there's a lot of other information you can glean from it. So highly suggest, for those of you who are looking for a tech elective and you want to get a little more in-depth understanding, taking linear algebra class, just a linear algebra, you can take linear algebra differential equations, but just a 3-credit hour linear algebra class gives you a lot of really good information. That was one of the best classes I took when I was an undergrad back in the day. Really learned a lot about stuff and really sets you up well. So we see it's 5 and 2. Feeling pretty good that our results check out. Okay, so it seems like we'll at least at the beginning have to go kind of slow for setting up matrices, right? Until people get comfortable. And then maybe what we'll do is we'll start, you're all will be better than me at it. So we'll start to we'll just start to maybe do less and less steps. So let's do this one. And we haven't been taught KVL and KCL yet. So I'll give you 5 minutes. You all do this problem for me with no KVL and no KVL, no Thevenin or Norton equivalents. Because we haven't been taught them yet, right? At least in this class. So let's do the brute force way.
So we have this replicating what we did other examples.
Exactly. Use KCL to solve for V1 and V2. Here, I'll even do this. So, oop, wrong button. I'll copy it over to whiteboard because I think as long as you all are okay with it, doing this one and getting a little extra practice, I think will be a good thing. How's that? Is it legible from back in T? How about TV land? Can you read it?
Yeah,
it's all good.
Yes, yeah, I can see
it's
it.
good.
Not sure how to do it, or oh, you're ahead of me.
Very good. I thought this was the first lecture, so.
Oh.
When I looked up on what was on white space. And then what we will go on over the first few days is not white space, so.
Yeah, I did that introduction one. Yeah, that's good. You want to come up here and show your work? No. Hold on. If we could give everybody a few minutes to. Oh no, I believe you. I'm saying, do you want to come up and show everybody else, or do you want me to do it, or? Okay. No, I totally believe you. If I wasn't saying you were wrong, I'm just saying if you're whiz bang at it, you're welcome to do it. You might have better handwriting than I do too. Got a couple more minutes. All right. Anybody get 20 and 20?
Yeah.
Anybody not get 20? Do we need to go through the problem in detail, or do you feel like this? You want to go through it? Okay. All right. So here's the process that I do, right? Maybe we can even do step by step, which is step 1, ID the nodes, which that's already done for us, right? That's a check. Step 2, assumed current directions. So based on V1 and V2, we're assuming that are going to be higher than reference. We're going to assume current is in this direction and current is in this direction. And since I is already demanded to go from left to right, from V1 to V2, then we're going to just keep that convention. So check. Step 3, apply KCL at nodes. So we're going to do the V1 node, right? We can start with V2, but we'll just go with V1. So this is the way that I like to do it. I think it's a little more efficient. So it's slightly different than using the sum of the currents in equals sum of the currents out. I just basically say the sum of the currents into a node equals 0. All right. So watch how I do that. The sum of the currents into a node equals 0. So 2 is current in. V1 minus 0, because that's reference, divided by 10, is that current into or out of the node? Out. So that is not a current in, it's a current out. Or it's a negative current, isn't it? So 2 going in, V1 minus 10, or V1 divided by 10 is going out. So I just put the negative there. Now I do the same thing. I see it's V1 minus V2. That's out of the node. So that becomes minus V1 minus V2 over 15. And that's going to equal 0. So you can do the sum of the current into the node, or you can do the sum of the current out of the node, or you can do the sum of the currents in equals the sum of the currents out. Any one of those is going to end up with the same result. I usually like to say the sum of the currents out of the node, but we'll just do the sum of the currents into the node for this one. So that's my first nodal equation. My second nodal equation, sum of the currents into the node equals 0. So 4. I see that the current through the 5 ohm resistor is out. So that's minus V2 over 0 divided by 5. Now, V1 minus V2, is that a current into the node or out of the node? V1 minus V2 going into node 2? It's in, so that becomes a plus V1 minus V2 over 15. If you use this approach, right, you don't have to worry about swapping V2 and V1 directions, which is probably what you were taught before. You just go ahead and write the currents the way it is, and then you put the plus or minus sign out front, and then everything shakes loose from there. Check. Step 4, simplify. Because we got a lot of fractions, and we got a lot of negatives, and we got a lot of this, and we got a lot of that. So let's go ahead and simplify a little bit. So I'm going to move the minus onto the other side. So I've got 2 equals V1 over 10. And then this becomes plus V1 over 15 minus V2 over 15, because I moved both of these to the other side of the equation so that negatives become positive. That's why you can see that I have a positive V1 over 15 instead of a negative, because I moved it to the other side. Same thing over here. I've got 4 and I've got equals, and I'm going to put this first one over here. So that's negative V1 over 15 plus V2 over 15 plus V2 over 5. I'm still not done yet. I still haven't simplified, but I didn't want to do this one big giant step without you all seeing it. So I've got to do one further simplification. So 2 is going to be equal to V1 times 1 over 10 plus 1 over 15 minus V2 over 15, factored out. Pretty simplified, almost all the way. And my next one, 4, is equal minus V1 over 15 plus V2 over 1 over 15 plus 1 over 5. Okay? Good with that so far? Now, my next step, step 5, put in matrix and solve. So now these are ready to go. So, and it doesn't matter the order of how I put the, currents or the voltages. I can do it on either side and it works perfectly fine. So I'm going to put my 2 and my 4, which is my known variables or my known values, and I'm going to put those on the left in a matrix. And I'm going to make this wide enough again so that I can put all the terms, because I know that that center matrix has to be a 2 by 2 matrix. And this one over here is my variable matrix, V1 and V2. Now, and as Robert asked, let's see if MATLAB is smart enough to do the calculations for us. So 1 over 10 plus 1 over 5 minus 1 over 15 is my first row. This is my first equation. Then I move to my second equation, minus 115, and then I have 1 over 15 plus 1 over 5. And that's my second row and my second equation. Pausing here to give you all a chance. Is this consistent? Or did you get to this point where perhaps you were able to enter this in, or is this like, whoa, you're going a little fast?
Yeah.
I haven't, like, used matrix, that was new to me, but it's making sense so far.
Okay. Yeah, that's good. So what you can see, hopefully, is you can pull in where these things are coming in. And if you kind of make it sort of, you can see I'm doing all those extra steps. I'm not just jumping right to a matrix, because I'm highlighting saying, oh, hopefully you can see where this comes from here to here. You can put the links there. Because once we have it in a matrix, then all we need to do is plug that into our calculator and solve this equation.
Hey, Paul,
Yes.
is that 1/10 plus 1/5? Is the 1/5 supposed to be a 15?
Let's see. Yes, should be a 15.
Okay.
Thank you. Yeah, because there are no 5s, right? It's a 15. I put a sloppy 15 there. So that's what I'm entering in my calculator. So let's enter it in. I'm going to move that all the way up. So MATLAB, I can see the whole result. And here's MATLAB. So I'm going to do clear and CLC so I can start all over again. All right, so my R matrix, or my R inverse matrix, we'll call that my G matrix, right? Because that's conductance, which is the term G, if you remember from physics. So my G matrix is going to be equal to, open brackets, 1 divided by 10 plus 1 divided by 15. That's my first element. My next element is minus 1 over 15. Move to my next row, so semicolon, minus 1 over 15. And lastly, I have 1 over 15 plus 1 over 5. Let me just make sure that that's, yep, we have here. I hit enter, and that's why you can let MATLAB do the calculations for you, right? Instead of having to calculate all that stuff by hand, just let MATLAB do it for you. You don't have to write all that stuff down. Yes, sir.
MATLAB, something we're gonna use on the text as well.
Great question. So for those of you in TV land, Luke asked a question, is that what we're going to be using MATLAB? Is MATLAB what we're going to be using on the test? And the answer is, it's up to you. You can use MATLAB or your calculator. Your choice.
But you can't use both.
Can't use both. That's why it was an or, not an and. And the reason why I say or is because in the past, I'm not saying anybody in this class, but in the past, people who, want to take the opportunity to not learn the material and get a couple breaks on the test, they would actually bring in both. They would bring in their calculator and they would use their computer and say, well, I'm going to use MATLAB if I need to. It's like, why? It's just a calculator. You've got a calculator right next to you. Why would you use MATLAB? If you're more comfortable using your calculator, just use your calculator. Don't use MATLAB. And come to find out, it was like, well, they were saying they were using MATLAB, but they might have been looking stuff up on the computer while doing it. So my philosophy is if you're willing to spend the time to practice and use MATLAB, more likely than not, you probably know the material and you're smart enough to realize that cheating is not going to help you. So, it's a little bit of a reach, but also I can walk around and I can look and see people having their screens up on MATLAB. It's much, much, much easier. So to me, it's the fairest I can make it. So it's up to you. That answer your question?
How can you like plug in what you're doing? Like, how do you do like matrix calculations on a calculator?
So depending on the version of your calculator, like a TI-89, you can actually enter in matrices there is a matrix tool where you can enter in directly. You can just use your cursors and scroll over and enter things in. Or you can specify a variable if you want. You can call it your name and you can say here, Toyota is equal to, and then you use open brackets, just like we did here in MATLAB. And then you type in the numbers with commas or semicolons, and then you close the bracket. And that's how you set up a variable.
Something like that. It's just
Let me see. You probably can enter some matrices. I did. You have the 86 too? Yeah. Oh, perfect. Okay, that's 10. It's good. So don't take this wrong. I don't have any. So it's totally up to you. So I understand if you use the 36 because that's what you're going to be using on the FE. So I get it, but the FE, the way the test is written, you don't do a ton of stuff with advanced calculations, where in our classes we tend to use a lot more. So using your TI-36 as a background kind of makes sense to do quick calculations, but I would encourage you to use MATLAB here. It just makes things easy. And what's that?
So there could require calculator or that's pretty calculator.
No, there's a required calculator in the FE, and you can take a look at it. And the reason why they don't want you to bring a super fancy calculator like you have is you could potentially write down some of the problems in your calculator and then sell them on the black market for millions of dollars, I guess. So you're only allowed very basic models. Like I think the 36 is one that they allow you to use now. Let's see. All you have to do is go to NCES.
I think they have it on so
Here, FE exam. These are approved calculators.
Yeah.
TI-30X, TI-36X are allowed. Casio, HP. That's it.
Yeah.
Those are the calculators you can bring. So if you want to use a TI-89, that ain't on the list. So you walk in and the proctor will say, let me see what materials you're going to have out. And you bring out your fancy calculator, say, no, you're not bringing that in. You got to leave it in your backpack or whatever outside. You're not allowed to bring those in. So that's why I'm assuming you all buy TI-36s or bought 36s because.
5%. Yeah.
Really? They're probably getting you prepped for the FE because if you played with one of those, the world is a very different place when you have a calculator that can do that. But sometimes those are very dangerous because it does so much for you. It can make you sort of lose what you're trying to learn. That's why I like MATLAB. It gives you all the power and then some of that, but you still have to be able to understand the material to enter in the syntax. So just my perspective. All right, whoops. So we got to enter this in. So we had our G matrix. We have to enter in our current matrix. I is equal to 2 semicolon 4. Now our V matrix is equal to G raised to the -1, or you could also go inverse of G. That works perfectly fine. And I multiply that by my I matrix. My voltage matrix is 20 and 20. Okay, everybody see how I did that? I entered that in. So I look over here, and V1 equals 20. And V2 equals 20. So the current I is going to be equal to V1 minus V2 over 15, 20 minus 20 over 15, 0 over 15, which equals 0. There's no potential difference across that resistor. So you don't get a voltage. I mean, a current flow through it. And the nice thing about matrices is I have V1 and V2 here. So those are based on these equations that I got right over here, right? I can also write an equation for I1 as being equal to V1 minus V2 over 15, right? Now I can add that into this equation. So you can see I have a third equation over here. So 0 equals V1 over 15 minus V2 over 15 minus I1. That's my third equation, right? So now I can set up a third equation, or I have my third matrix where I have 2, 4, 0, because that's a 0 in there. I have 1/10 plus 1 over 15 minus 1 over 15. This is equal to minus 1 over 15 and 1 over 15 plus a fifth. And my last equation, this is, oops, sorry, I'm doing too many steps in one fell swoop. That's equal to. So then my last equation, right, which is this final one over here, I've got 1 over 15 minus 1 over 15, but I have an additional variable. I have a minus I1, correct? But I don't have I1 in the two previous equations, do I? Everybody agree that I don't have I1 in the previous two equations? Most of y'all agree? I don't agree. I have I1 in those previous equations. Don't I?
Now.
I do now. I always did. I just didn't tell you that.
Yeah.
I was being top secret. So the thing is, remember how I said that matrix that you're going to invert has to be a square matrix? So I can make almost any matrix a square matrix if I start putting in zeros. So this is 0 I1, 0 I1, and -1 I1. And that multiplies to give me V1, V2, and I1. Don't forget that's the inverse. So let's add that one in and let's check and see if that result is consistent. So I'm going to clear my screen. Do that. All right, so I'm going to go up a little more. I guess I got to slide this down. And I'm going to do this all at once. I'm going to put the whole thing, because MATLAB can work with variables, or you can do it all like you would in your calculator, all on one line. So I'm going to just call this my VI matrix because it's got V and I in it. And that's going to be equal to my first open bracket. So I have 1/10 plus 1 over 15 minus 1 over 15, 0. Move to the next row, minus 1 over 15, 1/15 plus 1 over 5, 0. Next and final row, 1 over 15, minus 1 over 15, and minus 1. That's going to be raised to the -1 power. And then I'm going to multiply that by 2, 4, and 0. And when I hit enter, hopefully I get 20, 20, and 0. minus 0, 0. It's still 0, right? So this is another really nice thing about doing matrices. You can add equations very quickly and you can get results for other things without even having to go back and process it. So if you want to add those things in, you can do that really simply with adding matrices. I mean, adding additional elements. Sometimes it is not worth it. Like this one, it probably wasn't worth it. But you can see all I needed to do was add some zeros in there. Remember, I tricked you all. I said there was no I1 in those first two equations, but there was, but there wasn't. So you just multiply I1 by 0. If there's no variable in there, then that means it's just multiplied by 0. So it is there, but it's multiplied by 0. So it doesn't necessarily show up in the equation. So you can add that in and get the results that you want. Okay. How do you do a dependent current source? You just write one additional equation. So let's see if I can get this done. You want to try to jam it in? I think we only have 10 minutes left. Do you want to try to jam it in or do you want me to let you out early? Your choice.
Jam it in there.
Jam it in? All right, we'll do it quickly then. Tell me if I go too quickly. Jam it in there, yes. So here we go. So we'll do our approach here. We'll do our approach. So the V1 node, we have 15 going in, right? So that's plus 15. And then we have minus V2, V1 minus V2 over 1. And minus V1 over 2. That's all the currents. That sums to 0. My V2 node, I have 3I1 going in. And then I have plus V1 minus V2 over 1, also going in. And then going out is V2 minus 0 over 3, and that equals 0. And those are all my nodes. But if I look closely, I have 1 variable, 2 variable, 3 variables. So I have to write one additional equation, as we talked about with dependent sources, to make sure that I have that dependent source, and I write it as a function of the known variables. My I1 variable here is V1 divided by 2, isn't it? So I1 is equal to V1 divided by 2. So now I'm going to set these all up in my standard form. I have 15 equals V1 minus V2 over 1 and plus V1 over 2. This is, let's see, I have 0 equals V1 minus V2 over 1 minus V2 over 3 plus 3I1. And lastly, 0 equals V1 over 2. I can see that there's no V2 term, but I know I'm going to need it when I set up my matrices. And then this becomes minus I1, right? Because I move this over and I get 0 equals V1 over 2 minus I1. So I have to subtract I1. I'm missing I1 over here, right? So when I set these up in my matrix, and again, I'm just doing it this quickly because I'm trying to jam it in. That's going to be equal to, I see I have a 1 and a 2, right? So I have 1 over 1 plus 1/2 is 1.5 V1 minus V2. 0 is my first one. My next one is I have, let's see, I have V1. And then I have -1 plus 1/3. So I have -1 and 1/3. Oops, I'm putting in, I'll just, actually, I'm making it harder than I need to. Let's move the V's out here. So this is V1, V2, I1. This is -1. This is 1. This is -1 1/3. That's 3. That's 1/2, 0, -1. And that's doing it the quicker kind of way. That as you get better at this, you'll go ahead and solve for those. So you solve for V1, V2, and I1, taking the inverse of that matrix and multiplying here. Now, the other really nice thing about it is I can directly get what I1 is by doing this equation. If I did substitution of equation, I would have to substitute this into here, and then I've lost I1, right? So I'm going to still have to go ahead and calculate I1 after the fact. But over here in the matrices, I can see that I actually kept it in. So the actual calculation is going to give me the value of I1 that I need. So that's the nice thing. It makes it a lot easier, more efficient for you. Much, much, much better way to do that. Again, that was a little quick. I will pause here. If you have questions on how I entered that in.
Can you scroll back over?
The circuit?
Yeah.
No, it will actually wake up. Sometimes it does this with whiteboard. It falls asleep or it locks up. But everything is based on that process that we did, right? Step 1, identify the nodes. Step 2, specify current directions, assumed current directions. If you already know current sources, you know the directions are, you don't have to specify those. They're already specified for you. Step 3, start applying KCL at those nodes. Step 4, simplify, simplify, simplify. And step 5, set it up for MATLAB and then plug it in MATLAB and get your results. A lot of engineering is a process. Do step A, then step B, and then step C. It kind of turns us into robots, which may or may not be a good thing. It's probably a bad thing because nobody wants to be a robot, but it's a good thing because if I take a look at his work and your work, I can see that they have the same process. They are easy to follow. And if you're working with somebody else, they are, sort of familiar with this process of how to work problems too. So they can figure out what you're doing. But if it's haphazard and all this stuff, it's really difficult. I have a 5th grader and he's doing 6th grade math, which means you got to be a lot more, because he skipped 5th grade math basically. And so what ends up happening is that you actually have to show him a little more logical of a thought process because his teacher won't be able to figure it out. Like sometimes he writes over here, sometimes he goes over here, and then he's over here. And it's like the teacher's not going to, you can show me what you're doing, but your teacher is not going to be able to figure out what to do that. And I said, if I take this piece of paper away from you and come back in 2 hours and I say, show me how you did this problem, you're probably not going to be able to do it because you're not going to remember how you went from here to here to here. So I said, just try to be a little more logical and methodical, which is coming up with a process. He's not identifying that process. Step 1, write the problem over here. Step 2, move a line down. But that's the thing that will help, him, which also helps you, is kind of come up with a consistent process to tackle these problems. For fun, you don't have to do this for homework, but just try putting that in MATLAB, see if you can get it. Everybody here has MATLAB installed, hopefully. If you don't have it as of yet, that's fine.
How much storage do you say it would put it up?
I think it's 5 gig.
Yeah.
It is 5 gig.
5 gig.
So it's up to you, but I will say.
Do you have the link to download it on, or is it just fast?
No, the link to download it. I thought we did that. Did we do in class at the beginning?
UMaine software, UMaine.
Just go to umaine.edu/IT. See, it says UMaine software. And if you scroll down, there it is. It has all the details. If you don't want to install it, you can run it online, but you still have to have an account set up. And the problem is that you don't have a built-in debugger with your editor. It's not as easy to run script files. It's a little more cumbersome. So, it's up to you. And again, MATLAB isn't required in this class. It's just, like I said, it's instead of using a TI-36. Well, to me, I look at it as, you're a construction worker. And you can either walk in with your East Wing hammer and, you know, your satchel with a bunch of nails in it, or you can walk around with a Boss Stitch air nailer and, you know, do what, 10 times the amount of work in half the time. Doesn't mean you can't use the hammer. You can. But if you got to, you know, do, you know, maybe you're putting a roof on, you can just do a roof in a quarter of the time because you're not pounding nails the whole way. It's boom, 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 boom. And it ends up, if you set up the tool correctly, it does a better job. So a lot of it is better jobs. I used to say that about construction. Now it's plumbers, right? Used to walk around with one of those torches and a acetylene torch, and you would sweat all your pipes. Now you got all those fittings because everything is the crimp style one. So now they need special tools too, but they just look more professional when they're walking in with $5,000 worth of tools. The nice thing is MATLAB doesn't cost you $5,000. It's free. So keep that in the back of your mind. All right, we are definitely out of time. Any questions, TV land? Okay, I apologize for running a little bit over. Have a great weekend, and I will see you all on. I won't be in lab. That'll be Mark. Mark will be the lab who runs the lab, so he'll be there tomorrow.
Okay.
All right, y'all. Have a great day.
Okay.
Bye-bye.
Thank you, Paul.
Thank you.